So in this lecture, we'll be moving from the tactical artificial intelligence that as we've been talking to it into the more strategic mode. And so with that, we are moving from a more moment-to-moment thinking about responding or anticipating the environment. Instead, we are looking at thinking about the future and planning for the future, and maybe even responding to possible futures, right? And so this includes, maybe we as an agent responding to the other player or other agents, and treating that as possible futures and changes and adapting to that. So we make plans and we make strategies for long-term goals. So it's both a slower, longer-term period of time, but it's also potentially more complicated in some ways in terms of the actual thinking process or the computation that has to happen. So kind of the primary point at which we'll talk about most of this is in state machines. So state machines are a way of thinking about the way the process works. And if you're not familiar with state machines, you can think of them like an assembly line, or an assembly line with multiple paths, right? So here we see just a simple assembly process, an assembly line, automated factory where people are actually in there adding parts to it. And each of the women in this assembly line has a particular task, right? She's supposed to add some component to, I think, a typewriter in this case, or something like a typewriter. And she adds those components over and over. And so the person in front of her adds the component that she's responsible for. It gets moved on to the next woman in line, and then that woman adds the component that she's responsible for. Assuming everything works out, by the end of this line, you have a fully complicated, put-together machine that might happen actually fairly quickly. So part of the usefulness here is really the parallel nature of it, that we're actually operating on, if we have 4 women there, we're operating on 4 typewriters at once, but the task itself is maybe not as complicated as if one woman was trying to put together the entire set. So it's actually a series of simple tasks that can be iterated on very quickly. So that's kind of the notion in a state machine. Each node really has a very simple task, but when you put them together, you wind up with something fairly complicated. Now there's also a decision process. So you could imagine in this case is very linear, right? The one woman moves to the next woman and so on in the assembly line. But if we wanted something more complicated, we might say, well, if the typewriter has some defect, we might move it to a repair line, and it has to go through a repair line and then come back into the main line to get fixed, right? And so with something like that, then we'd actually have a decision process where one woman's entire job essentially is just to analyze how is the typewriter looking so far, and is it valid or not. So if we consider the sort of end state of all machines, can we make a state machine that is complicated enough to be human? And this was actually proposed philosophically by a man named John Searle, who proposed what he referred to as the Chinese room problem. So the idea here is that, again, it's people following simple instructions, and if you create a book with Chinese translations in them, right, and so you have non-Chinese speakers looking at Chinese characters and iterating it and creating an alternate Chinese character for each one of those coming through. So the point is that we have a complicated set of characters that span a range, much like we do with bytes in a programming language. But the people operating on them don't understand them at all, right? They're doing very simple mechanics. And the idea is, well, if you were to insert a phrase in Chinese on one end of the machine, have people go through and look at the symbols and replace them, and maybe multiple people in that room replacing symbols and swapping them out, then at the end you get a new set of Chinese symbols, and does it appear like they made a response that made sense, right? Is there enough information presented or responded to that you could carry on a conversation, assuming you spoke Chinese and you were outside the box? Could you carry on a conversation with the box, even though everyone inside the box does not speak Chinese and there's no intelligence? So John Searle's point here is sort of an ad absurdum kind of argument where, of course, this is an intelligence, because the intelligent people are not doing anything intelligent at all. On the contrary, you can imagine that if you have a few million people operating this way, that you start to arrive at something that resembles intelligence, if not actual intelligence. The sort of corollary argument really is something like a colony of bees or a colony of ants. And so each of the ants in a case like that are actually following very simple procedures. But an ant colony and a bee colony are both able to thrive and survive, assuming toxins are not in the environment and killing all the bees. They're able to adapt and move and work almost as a single entity with sort of a distributed brain structure across all of the beings in the structure, and do some fairly complicated and intelligent tasks, intelligent at much higher level. And so we're really, kind of stealing the thunder from the humans by removing all of their intelligence for John Searle's problem. But it does relate to the state machine. And so as we see, computers start to become more complicated by, say, searching through larger and larger state spaces and are able to solve bigger and bigger problems, all of the Google or IBM method of having a large state space or searching through all the chess answers, we start to see something that approaches at least difficult intelligence, right? A challenging opponent at the very least in terms of chess, or something that can help us search very, very functionally. So it's hard to throw out that argument entirely, but it still is a question of what level of complexity is in our state machine, right? So certainly simple text replacements might not be enough, unless some of those text replacements also contain some memory and some other things in them. Okay, so let's return to our standard loop. And so even though we're talking at a strategic level, we're still going to consider this loop, right? And so the sensing is at maybe a higher level, a slower speed. We say, rather than trying to sense moment to moment, we look at sort of the trajectory that our environment is taking place or the game is taking place, and make larger decisions about how the players are positioned within the field, things like that. And then our decisions end up being more like commands over time, right? I need you to go to this location, or I need you to kill that enemy, without giving specifics on how to kill the enemy. The goal is simply just to kill that enemy, right? Because that one's important to kill for some reason. And then the actions are, by their nature, more complicated as well. So let's take a look at how a state machine would help us to solve those kinds of problems. So in the first case, we do need to understand now the difference between standard assembly line and a real state machine. So again, a standard assembly line is going to follow just the expected path, and pretty much in the worst case with an assembly line, we mentioned there might be a malfunctioning typewriter. What we want to do is actually have multiple paths that represent sort of good and bad outcomes. So in a standard assembly line, we might have, say, a bad egg like we have here from the original Willy Wonka, and she just gets disappeared out of into the system. We don't simply reject bad states with state machine with the AI, and in fact we sort of expect them, right? So the player is going to overcome us in some sense, and so the bad states for the AI, if we think of them that way, are really when the player has started interfering. And so then we need to consider where we go from there, right? So there's multiple paths, and really what it ends up being is we do have a lot of linear paths in our state machines, but we also have branch points that sort of send us on different versions of these linear paths as we move through the states. So let's take a look at a fairly straightforward kind of path. This is really the linear path here, where we kind of move back and forth, right? And so the standard state machine is especially functional for regular expressions. So if you've probably seen this if you're in computer science and have taken enough classes, that state machines are very good for the kind of symbol replacement as we were talking about with the Chinese room, where we detect a symbol and then either leave it or replace it with a new symbol by essentially emitting a symbol out at that point, right? So we'd say, well, if I'm in this first state, I'm going to write the letter A. And then if at any point I see a B, I'm going to switch over here, right? And I'm going to start emitting characters of B. And what we kind of assume is that we'll stay in the state, and so we'll see other characters. So let's say we're here again, and we're emitting A's, and we see C, D, E, or any other character in the language, or maybe even ASCII characters, regardless kind of what we allow to be input to the system. Anytime we see one of those characters, we'll switch to A's, right? But if at any point we see a B, then we swap over here and start emitting B's. And then we stay at B's until we see another A. So if you were to imagine the alphabet, we would see A once, then we see B, and then we see 25 letters B, and then we'd see an A as we cycle back to the beginning of the alphabet and we come back to A. and then we'd see Bs again. So it'd be A, 25 Bs, A, 25 Bs, and so on. And for any pattern, we might see a different kind of thing. Now, the one thing I've left off here is often state machines also have kind of an end state to say, well, if I see, say, a Z, I might go to an end state over here. But really that doesn't change too much. We can imagine an infinite loop, which is most of our AIs are actually infinite loops that sort of don't stop thinking at any point because we want them to keep thinking in some sense. And so we don't necessarily consider that, but there is usually an end state as well. So we'll have at least the start state over here is our black circle that kicks us off and picks which state we begin with, and then we'll have some decisions happening, and we'll generally assume that we're going to stay in this state until some other kind of input happens. Okay, and one last thought before we leave here is we normally don't think of emitting a character with our AI. Rather, this is kind of the action that we're going to take. So this is helping us to both detect the environment and to decide what we're doing, deciding which state we're going to end up in as a result of what we detect in the environment. But then the actual active part is an action in the game, like moving to a location or attacking or something like that. Okay, so here's a fairly simple state machine again. This one actually represents the cylinder that we used for the first part of the book chapter. So what we had is essentially a patrol behavior from our cylinder, which was, and we do see an end state here. So we have a start state here and an end state over here, which is when our character dies, right? Our cylinder dies in this case. And we go through and we begin by patrolling. And so at the beginning of our state with our blueprint, we are in a position where we're moving back and forth, right? And so we don't necessarily leave this state at any point. And in fact, even when we get hit, we don't really stop patrolling. We might even think of this as being maybe a slightly different sort of version of the state over here, but we'll look at it as a new state, right? So this is our secondary patrol state, which might actually include that we got moved a little bit based on the fact that the bullet hit us, right? And we're going to continue to patrol, but we also changed our material. So we got hit, so we stayed in this patrol state. We sort of assumed that if nothing else is happening, or the world is, regardless of what else is happening in the world, until we get hit, a particular activity, then we follow this line, and now we're over to the change material and patrol state. And then we get hit again, and we make an explosion, and we make a sound, and then we destroy our character. Right? So this one actually did have an end state because we did destroy our character. And of course we're not actually doing much thinking here, but there's sort of a very basic level of thinking. Right? So the goal with state machines is not necessarily to program as much as to understand the program. And by understanding the program, we can sort of almost work entirely in state machine space and then translate it back into what the program should do. So this helps us both understand what exists in the code, but also to modify the process, the logic, the thinking that's happening at this level, and then transcribe it back into the code. So if you feel comfortable with, and you should try to make yourself comfortable with how this translates into the code so that you can understand if we were to make changes to this, how those changes might affect the code and therefore affect the complexity, because we're going to start looking at a whole lot of state machines here and how we might get more complicated behavior out of them. So let's see a real kind of situation here. So with a standard enemy attack, and we will actually build an example of this one, then we have a patrol behavior, and when we see an enemy, then we will go into an attack mode, and we'll stay, so again, we'll be in the patrol behavior the whole time until we see an enemy. So absolutely nothing else really affects us other than we're going to continue to do this patrol. And the patrol is really following waypoints and doing some of a certain set of tactical things that we would do under patrol. Right? And then we see the enemy, and when we see the enemy, we move into the attack mode. Now the attack mode is an entirely different way, right? You can think of the patrol as being move to waypoint A and arrive, and then move to waypoint B and arrive, and so on, and do that in a repeating pattern over and over again. Whereas the attack is seek the player, and when close enough, attack, like swing your sword, or do an attack animation, and also apply some damage to the character, or just simply run into them and cause some damage that way, depending on how you structure it. And this continues until either there's no enemy to be seen, right? So you no longer see the character or the player, maybe because they died because you successfully killed them, or they managed to run away from you well enough even though you were doing the seek behavior and trying to follow them. They manage to get behind something or to move through a wall or to get behind a door that you can no longer see them. And so it breaks line of sight, and so now we don't see the enemy anymore. So when that happens, we go back to our patrol state. We actually go back to A and B over and over again. We simply move to those spots in the world, right? Arrive to A and then arrive to B and so on. The other possible paths, so there's actually two paths out of this node. One is that we no longer see the enemy. The other is that we have low health. So if our health drops below a certain state, then we move down this path and we go into the flee state, and this again becomes our flee steering behavior. So we start moving away from the player in order to avoid them, right? So we move in the exact opposite direction of wherever the player is. And once we no longer see them because we've happened to move through a door or just separated ourselves far enough away from the player that we feel comfortable, then we can go back to our patrol state. And so given all of this, you get sort of a very minimal level of AI, but from this you should start to make yourself comfortable with the idea that you can do where you would start to break this up and how you would make the transitions and the branching points, and start to imagine how you would construct a blueprint that does this. So again, just to reiterate, the patrol node really does a seek and arrive to a known location, right? So those are like, say, an A and a B point in the world that we can define, and we can just simply do a seek, much like we already saw with the previous examples of seeking into the world, or really arriving, right? So with a patrol, we'd probably arrive at that point. Once we do arrive, and we finish landing on the spot that we're supposed to land on, then we'll turn around and go back to the other spot. We could even do this with multiples, so there's not a reason that it has to be A and B. It could be A, B, C, and D, and so on. And then the attack behavior is pursuing the player. So in the very simplest case, we might assume that if we touch the player, we cause damage to them. With certain simple games, that is the case. And so just by pursuing the player, we will end up running into them and maybe causing some damage that way. So that's a very simple version of it. And of course, with just a little bit extra complexity, we'd say, well, we'll go into pursue, and then when we're in the right range, we'll swing a sword, right? We'll just do one other activity, but we'll continue to pursue. So, the swinging sword might stop us for a moment, swing the sword, and then go back. Or we even, might have a remote attack, like a projectile or something like that, or a magic spell. Let's get set up for State Machine in Blueprints here. So I'm going to move my ball over to the side over here, my starting ball. This is really just to allow my camera to be in a good position. I'm going to have the enemy over here, and so when I press play, I want to be able to just see what's happening, maybe move very quickly over to this location, or move quickly within this location. Let's go ahead and put a sphere here, and then we're also going to put these target points that I'm searching for. So in this case, they're not going to be obvious, so you have to use the search bar to find them. But then once you do that, they are pretty much just specialized actors for this kind of purpose, where we want to have a position somewhere in the space that we want to go to arrive to. And so we'll come back to this, but for now, let's go ahead and call this guy enemy. And I like this mirror plane material for this. Looks a little bit enemy-like. And what I'll start with is, before we do the state machine, let's go ahead and set up a physical version of the steering behavior to have this guy actually roll, we'll have it do linear velocity. It won't roll necessarily, other than the friction that's going to be involved. But we'll have him roll over and arrive at this spot here. So let's create a blueprint. Go ahead and put it under the rolling ball blueprints here. So now we've got our enemy blueprint. Go ahead and get rid of the ones I don't need. Okay, and then from here we'll go ahead and set up the arrive behavior. So to start with, I'm going to create a target point, and I'll just set this up as an actor for now. I'm going to call that patrol point. Actually, I'll give it a capital P here. I'm going to make that public so that I can set it to my target point over here. So I'm going to look at my enemy character, find the variable here, and then set it to target point 1. Okay. So when I search in here, this is giving me a list of all of the actors within my scene currently, and I'm going to set it to one of the specific actors, the target point 1 in this case, to get it there. And so it should go here. And so we expect our ball to arrive over there as part of that. So let's go ahead and do this. We've done this a couple times, but we'll have it, there will be some simplicity here, some things to make it easier. So I'll move through this, but we will skip, the video is going to skip a few different times as we go. Now one thing I need to do here, so I'm going to use the distance, and we saw previously that we used a distance of 100, or subtracted 100. I am going to subtract 50 in this case, and that's because when we move our ball, notice that the ball is centered here, right? So the origin, the object reference point for this ball is centered in the center of the ball, and the ball is 50 centimeters tall, right? Or that point is 50 centimeters off the ground. So if I'm moving here, then although I'm going to get to the point, right, I'm going to move on to my target point here, I can't get any closer than 50 centimeters away from that ball. I mean from that spot on the ground. So in order to account for that, I will just simply, as we saw with the previous steer behavior, I'll just subtract from the distance that I'm using here and use that to help determine how close I am to that point. So if I'm 50 points close to that point, it means I'm directly above it in some sense, or 50 centimeters away from that point. Okay, and then as we've done before, I will set up a slowing distance, which will be a foot. We'll also need a max speed as we've had before. Go ahead and set this default value to 400. Actually, just to be... And I forgot to set my slowing distance, so I'll go ahead and set that now. I'll set that to 150 centimeters, so about 3 ball lengths away, or ball radii away. And then here's where we're going to vary a little bit. So I'm going to take my static mesh component, I'm going to get linear velocity. So I'm getting the physics linear velocity from my static mesh component, and then we're going to, so rather than the velocity that we've seen before, we're going to use this velocity and subtract to get our steering direction. So this now sets our steering direction. I'll go ahead and set a variable for that. I'm calling it a force. That's a little bit of a misnomer, but we're going to go ahead and keep that way, even though we are continuing to. So we've got our steering force set up using the physics linear velocity. Now we're going to go in and set that linear velocity to update based on the steering force. Just to keep under control here, let's go ahead and put a comment block before we move further. So as we did before, let's add in a sequence here, so that we can easily separate these out. So we'll have this as our first level of the sequence, and then in the second level of the sequence, or the second state, or second iteration, we'll go ahead and we're going to set the linear velocity, and we're going to set that based on our update. As much as we did before, in fact, I'll just copy that same pattern. So we're going to get the physics linear velocity. It's actually the first step here. Then we're going to add our steering force. Use the clamp vector size here just as a simplification. And so really it's a very simple process, of course. So it's not a real force because we're directly modifying the velocity by this force rather than adjusting it based on our mass of our object. We could actually modify this steering force divided by the mass of the object, so you can, if you want to see that, physics So we can get the mass that way. We could use that as a divisor. I'm not going to worry about it in this case, but certainly it's an option that you have available if you want to consider it that way. So let's take a look. Let's see how this runs. Let's make sure to compile and save both, and we'll see if anything's missing. Let's make sure to connect up our velocity, our vector, our final actual steering force here, so to make sure we're setting our linear velocity. So what we're expecting is that when I press play here, the ball should start rolling, and it doesn't. Okay, so there is an important detail that I forgot. It turns out when we take the static mesh component from the side over here, where we pulled the sphere from over here, we start with a non-mobile, so we start with a static or potentially stationary object. We need to make sure to set it to movable. So this, of course, is a step that you might forget as well, so don't forget to do that. To check it, remember that static is generally used for like the environment, things that aren't going to move, like the walls and fixtures, because then you can optimize some of the things away. So you can reduce the complexity, you can simplify the physics and all that kind of fun stuff. And if it's movable, then you want to set it movable. But by default, a lot of things are going to be set static. So certainly something to keep in mind as you're doing this. Okay, and then the other thing that I forgot in addition to the movable is we want to make sure that we're actually simulating physics here. So I'm going to go ahead and not only simulate the physics, but also set our linear damp and our angular damp, just to give us a little bit more there. And I will set our material to one that we are using for our ball. So all of this can align very similarly to the ball that we had before. So let's check that. And we do see that our ball rolls forward and arrives at the spot. So that is what we expected to happen. Now to set up our state machine, I'm going to use something that is inadvisable under normal circumstances, but we'll go ahead and use it here. It is possible to create enumerations in certain ways. It is non-trivial with blueprints, and so we're just going to use a string for the time being. But it is generally not considered a good idea to use a string for a state variable, simply because you're going to have to do a lot more work to figure out what your value of your state is, because a string comparison ends up being fairly problematic. Also, it's easier to make mistakes. But we'll go ahead and we'll set up a patrol 1 here, and then when we are doing the first part of our sequence, so the idea behind the state machine is, in this case, we are going to switch what kind of steering we want to do as part of the state transition. So that's only going to be this first part here. Everything about the velocity update will remain the same, so we'll kind of move that down here. And we're really just going to change this. And so in the first instance, what we'll do is simply, depending on which state we're in, we'll change our patrol point. So it'll really be the same state, but we'll go ahead and set that as part of it just to get the example going. So we're going to do a switch on string. String will be our state value. And then what we'll do is we'll add pins to create new case values. So we can create them over here, we can edit them that way. I'm just going to add the pin here and then start modifying it. So I'm going to say patrol 1 and patrol 2. And then we're going to create an attack state, but we're not going to use that necessarily right now. We will fill that in as an exercise. And we could also have a flee state. Okay, so this activity up here is actually our patrol 1 activity. Let me go ahead and ignore the default. In fact, I'm going to get rid of the default pin, so we won't have that as an option. What I'm actually going to do is, if I am in patrol 1 here, I'm going to create 2 new variables. I'm going to create patrol point 1, which will be a actor, and patrol point 2. So these are going to be public actors. And we're going to set, as you might expect, if you're following along here, that we will, oops, I need to make sure I compile. We'll set, or we can leave the current patrol point the same, that's fine. I'm going to set patrol point 1 as that, and patrol point 2 as that. So the first thing we do is, before we come in here, we're going to get patrol, oops, so we're going to set patrol point. We're going to set it to patrol point 1, this way. We're going to do the same thing here. Now what's interesting is in both of these cases we could actually use the same value here to get us to moving in this direction. However, we do need to set up one other thing, and that is that we want to check how close we are over here. So we're going to take a look at our clamped stopping distance, and we're going to use that to decide when we're close enough. Okay. So what we'll do is say, so I'll pull the float value here. I'll say when I'm less than about 10% of my stopping distance, so around 5, I'll consider that good enough. So what's happening here is I'm on the patrol point 1 path, right? So I'm on patrol 1 here. And if I find that I'm close enough, because I'm checking the results of my moving to arrive over here, and if I am close enough, then I'm going to change my new location, my new state, to patrol point 2. So that's going to move me into this state. So I'm going to do the same thing over here. Actually, I'm going to set this so that this is my maneuver here. I'm going to do branch. Now the other case, so I've got my state transition here. The other thing I need to be aware of is if I'm not going to transition, I still want to set my linear velocity. So I actually want the false behavior to go over here as well. And technically, I could either allow a state, so if I just set the state transition, I could say I'm not going to bother setting the velocity, or I could set the velocity for 1 frame. Essentially, it's going to continue to do the one last velocity position update here, which is fine. So we end up always kind of changing this regardless of what we do with the branching here. But the only difference is that we, when we hit these branches, we swap our state out. So let's put a comment block around this. And let's test it out. So you see we move to the first state, and then once we get close enough to that one, we move to our second state. Of course, when we're close enough, we move back, and so we have a proper patrol behavior as we look for. And you could, if you wanted to, set the threshold here to different values, say make it somewhat larger if you don't really care that they get all the way to their patrol point, or continue rolling that way a little bit before they start rolling the other direction. So the state machine we started to create here, it's this one to some extent, but we're actually doing this here. So this is a slightly more complicated setup, or at least a slightly more communicative one. It says we've actually got 2 patrol states. One is our patrol position 1 and our patrol position 2, and then you see that we've also got attack and flee. And notice that these names all then line up exactly with what we did in our state machine, right, in the code. And so what we've done so far is simply create these 2 paths here. We've set up patrol 1 and patrol 2, and we're moving between them, and then we've done all the work of handling the patrol 1 and patrol 2 inside the code. Right? So to expand on this then, we would need to add a C enemy, which both of these would use as a transition, and then that, much like what we're doing here when we are close enough, so this is our comparison for close enough, and then we do a branch based on that. If we then see the enemy, we have another comparison here to see how close we are to the enemy, or if they're within a range. Then we'll branch and we'll set the attack state to true, right? And then for the flee, we would know we would need to devise low health, and we'd actually have to make sure that our enemies have health and that they also get damaged in a way similar to the player, and that if they have low health, then they start to flee, right? Or if they flee and they're no longer close enough to the enemy, then they can do it that way. And of course, for maybe this purpose, we'll use seeing the enemy as simply being close enough to the enemy, much like we're close enough to our patrol point here. So now that we know how to take a state machine diagram and put it into code, or vice versa, maybe improve our diagram based on what we need to do in the code, in either case, we can understand that these state machines are a communication mechanism. They're a way of understanding and deriving behavior without necessarily needing the code. So it's a way to communicate and talk about what the state machine is going to do. But then it's very straightforward to transition it into the code. Now that it, of course, takes quite a few nodes to do, and it takes a series of steps. We just saw that, but it, only took us about 15 minutes or so to actually step through that process. And once we have a lot of the infrastructure in place, all the steering behaviors and the state machine switch behaviors happening, then just adding new transitions between the nodes is very straightforward. And of course, adding the attack and the flee will take some time as well. But again, assuming we have those, let's see how we then might look at increasing complexity. So actually capturing some more complicated kinds of behaviors simply by adding a few new nodes or a few transitions between the nodes. So one way to do that is to have a reaction time. So we've talked quite a bit about reaction versus anticipation time, and the fact that when we see something that's unexpected, it might take us up to a half a second before we actually react to it correctly. So having our enemy see us and immediately start moving in our direction doesn't feel very realistic. Instead, if we have a pause state in some sense, so we sit here and wait for half a second before we move on, when we see our enemy, it actually will look like the enemy has sort of been surprised by us, right? So then they're reacting to us, and so it adds a little bit more. It's also possible that if we were doing animations, we could add in a surprise animation at this point, which takes around a half a second, and then moves into the attack. So just that gives a feeling of more human-like behavior, and actually gives the player a chance to deal with the fact that they've been seen, right? So in a game where we may be trying to be sneaky, allowing for this reaction time actually allows the player to deal with the situation a little bit, the changing situation for them in their game. So they were trying to be sneaky, they're no longer able to be sneaky. The enemy has seen them, they now need to decide if they're going to hide or fight or what they're going to do. And so this is one of those cases where we're actually adding sort of an intentional weakness to the enemy. The enemy, because it's an AI, because it's a computer, could react instantaneously much faster than a human could if it wanted to. But we're trying to build in sort of those, as we talked about before, the kinds of designed weaknesses to make the enemy potentially beatable. We could also add a simple memory. So this is a single state memory, which is, we might be in our patrol state, and if we see the player or see the enemy, however you want to phrase that, we go into attack mode. If we no longer see the player, now we might go into either a searching or maybe a patrol in the area that we saw the player. We might do a wander state within that area. We might act a little bit more aggressively, right? So this might be the kind of case where in a game where the enemies are now looking for you, right? So you've gone through the attack mode, and this is just, we no longer see the enemy, they successfully hid, but we're not going to go back to our normal patrol state. We're not going to pretend that it's a normal state. What we're going to do is go to a slightly different patrol state. And again, this is not much more complexity than what we've already had. We're really just creating maybe 2 new patrol points that are I need to, or maybe 4 or 5 patrol points or something like that, right? That I'm going to do a little bit more thorough checking. I'm going to look through hidden areas, and maybe if I know, I'm working with my level designer, I know where those are, or common hiding spots for the player. I might use those as part of my patrol, and so now it becomes a little more aggressive. And again, there's really no change here in terms of the states, the patrol, and everything. It's really just the transitions that are changing that make things a little more interesting. This one takes a little more work than before, but again, the notion here is not too much different, right? So if we were to keep a list of our allies, or keep a notification, some way of noticing those targets, right? Those actors that represent our allies. Then when we see the enemy, we can set a variable in those other allies, and we set a variable is notified in there as a checkbox. And so if at any time, while we're in our patrol state, the is notified is set to true, we transition to a move to ally state. So we're not necessarily moving to the player. We don't know where the player is, but we do know where our ally is. So we know which ally may be notified us. We might set both is notified and who am I, or maybe we'll set a position to move to, right? And so we're just simply arriving or seeking in this state here. So again, not too much different than the attack or the patrol in terms of the movement characteristics. But by moving close, we're actually setting up a situation where we're very likely to see the enemy, right? And so what we can do is say, and here we're kind of cheating a little bit. We're just saying move to the ally and then immediately go into attack mode. So immediately start just going after the player. We'll assume that we can already see the player. We might also say, well, let's move to our ally, and if we see the player here, then we'll go into attack mode. If we don't see the player, then we'll maybe go back to our patrol and we'll assume our ally was done, right? So that's maybe a few different transitions here. But we could go into attack mode, and so of course, even if we're in attack mode here, if we immediately don't see the enemy, we're going to go back to our patrol. Or if we start getting attacked by that enemy, we'll go that way. But most likely, by moving close to where our ally is, who's already seeing the enemy and already trying to attack him, we'll most likely see the enemy as well. And so it's a very simple case here, and you get a very much more complicated kind of behavior. You actually get like a squad of enemies that will then be able to attack, right? And all that we're doing here is just keeping track of who our allies are and setting one variable on those allies, or one or two variables on those allies, to let them know that they need to come moving in our direction. Again, not much more complexity than what we're already doing. The node in here is exactly the same as everything else we've done. The only difference here is just being able to set a variable on the other player, or on a different actor character. Now we've looked at state machines at this point. We've looked at how to create a simple one, how to talk through the diagrams for more complicated ones, and hopefully you start to get a sense for how you might build one of these more complicated states into your AI. Or into your character, simply by adding transitions. But what if we were to start looking at, say, adding 1,000,000 states, or potentially many more, right? Now you might say that we can't really represent 1,000,000 states, and you'd probably be right, because it's very difficult to actually draw all of those lines. However, we could, in some ways, do that implicitly, right? So we can, by structuring, especially in a game like chess or Go, we can actually structure each board state as the current state in the world, and transitions as moving certain pieces, right? And so rather than explicitly doing this, we create an implicit state machine. We say we know at every board state that there are certain numbers of moves that are all possible. And what we want to do is then look for maybe the transition that we want to make, right? So what is the branching condition? Which is the move or the piece that we want to move? And so you can almost think of the way that we create these more complicated AI states as sort of understanding that there are many branching conditions, and we're really trying to figure out which one we want to pick. So rather than saying, are we close enough to the player, or are we damaged or something like that, what we're looking at is which one's going to cause me to win, right? And so now we're branching by going further down. And so a lot of what these do is a method known as mini-maxing, where I'm going to make a move on my state transition to say I'm going to pick the one that I think is most likely to give me a win. And then you're going to pick a move that's most likely to give you a win. And so when I'm trying to make the decision, when I'm trying to make one of these branch modes that I've not created explicitly anymore, I'm just in a state and trying to figure out how to transition to the next state by making a move, I'm going to pick the move that both maximizes my chances of winning and minimizes the chance that you're going to win. It actually makes it so that all of the moves that you can make are the worst that I can make possible. So not only am I trying to pick the one that makes it the best case for me, my one move, but I'm also looking at the next move ahead and saying, which is going to be the one that's worse for you. And I could look several moves ahead, right? So if you remember, or if you think to how people talk about the way chess masters play, they actually look 4 to 10 to 15 moves ahead. And so we can have the AI do the same kind of thing. It could predict, it could say, well, if I picked all of these different moves, and you picked all of these other moves, then I have some pretty heavy branching and a whole lot of states that I'm going through. But I can keep those all in the computer's memory. And what I'm doing is looking and seeing, okay, well, what are the possible board positions? And I want to pick a board position that's the best. I want to pick the one that makes it worse for you and best for me. And I could potentially go all the way to the end of the game, right? So try to go that far. But of course, it's very difficult to do that. And so there's actually ways to just evaluate current board positions and determine that they are good or bad as part of the search. But again, if you've got Deep Blue, if you've got a supercomputer, maybe you can actually do a lot more searching. You can actually search through many more board positions, or you can search through many games and decide statistically whether or not a board position was actually that good. Yeah, so just to review here, again, we're almost looking at a state machine in both of these cases, but we're looking at a state machine that is potentially, we can't really humanly draw out the diagram, and we can't humanly actually write the code assuming actual states, right, that we're actually going to keep track of a million different states uh, as possibilities. So rather, instead, we build something where we sort of allow it to construct implicitly. So that's the way these kinds of things work. Or that's kind of the next level of advancement. So we can't always have a supercomputer at our hand to let us do millions of states. So one of the next ways that we handle this is to actually do sort of multi-layers, and this is something that Left 4 Dead pioneered, which is we actually have zombies which probably act very similar to our kinds of AI that we've done so far, right? So we said, the zombie is probably going to do some kind of wander patrol, probably more like a wander, like a random wandering around. It's going to pick a random spot to move and then move to that spot. So that's kind of the way you do a wander versus patrol. You just pick a random spot and move to it, a random nearby spot. And then when you arrive at that one, you pick a new random nearby spot and you move to that one. And then if they see the player, they attack. And maybe we allow some smart zombies, if they start to get damaged enough, they'll flee, right? So that may be the extent of our intelligent zombies. That's all they're doing. And so, sure, we could have a single state machine, and we create an instance for those, and now we have, say, several hundred zombies all moving around following that kind of instance. We might even do the communication thing, right? You might have a zombie that starts yelling if it sees the player, and the other zombies realize there's a player going on, or that kind of action is happening. But what the Left 4 Dead and the multi-level AI does is there's another AI which looks at the situation at a higher level. It's a little bit like we've already talked about with sort of tactical and steering and just managing like the moment-to-moment position, and then the strategic level that we're talking about with what state are we in, and how do we move to the next state? Are we in a wander, or do we see the player? So the higher level then is the director, which then decides things like, is the player getting bored, and should I have a whole horde of zombies start attacking the player? Right. So that's why it's known as the director. It actually tries to look at the state of the game, and it doesn't necessarily control the zombies. It simply creates new instances of the zombies. It spawns them in the world, or removes them. If the player's getting overwhelmed, it might actually create some other kind of situation that helps the player to survive, to keep the game, keep the player from being overwhelmed, but also keep the player from being bored as well. And so that's kind of the director's job. It's a state machine at a higher level where the nodes are maybe a little bit more complex. The nodes are, is the player bored or not? And then if the player is bored, or really the transitions are, is the player bored or not? And then the nodes are things like create a zombie horde, or create something to save the player out of the situation, or help them recover out of the situation. Maybe even spawn some extra ammo or something like that, right? So that's a way of handling complexity without necessarily having to have a lot of, or it's a new way of handling complexity where rather than having a huge state machine or a huge implicit state machine, we just start creating more and more levels. So we could say, well, this one is keeping track of whether the player's bored. We might also actually think of it as we could have a general, right? So we have our troops down here, which again might have some strategic level of control themselves, but we might, as the general, say, well, I need to have reinforcements over here, and I might need to have reinforcements over here, or I might need some archers who have a certain kind of attack method, and some infantry that have a different kind of attack method. And so I'm making choices at that level. I'm still a state machine. I'm still maybe 10 to 15 different states, but my nodes might be somewhat more complicated in terms of moving whole hordes of units. But then those units themselves are complicated on their own level, and so you can get to those kinds of interesting levels of behavior by doing that way. So fear is another one. So this is actually an interesting new kind of technology where rather than creating the states at all, we're kind of doing that search, but we're actually pathfinding through the state space. So this is a method known as goal-oriented action planning. And the idea is that you have a goal, like kill the player, and you have a variety of actions that are possible, much like we talked about with the moves of a chessboard. But in this case, it might be moves might be pick up a weapon, or find some ammo, or flank the player, or shoot the player if you see the player. And what this is going to do is determine that, given this current state of the world, given where my fellow players are, I'm going to search using the A-star method to find what I think is probably the best set of actions that will set the world in a certain state, right? So if I need to shoot the player, I need a weapon. So I need to find a weapon if I don't already have one. So I might actually pick one up off of a guy on the ground, right? Even though it's an enemy in the game, an AI, they know about weapons and they can pick them up off the ground and use them, or they can pick up ammo from that if they've run out of ammo. They can also move to interesting cover positions, right, as part of it. So they might say, the state of the world is I don't want to get shot, so I'm going to move to a cover position. So it's a variation on the idea of setting up an implicit state machine again, where we're not really encoding all of the states. We're actually just encode the kinds of actions that we can do. And then we determine whether or not those actions are even possible from this state or not. Am I near a weapon? If I'm not, then that action isn't possible. I can't pick up a weapon. Or is the player, do I even see the player? Maybe I need to move to a patrol state to even try to find the player in the first place. And so it turns out that, with enough states, with enough complexity, fear is actually still recognized as one of the best AI that has been created. And there's some video links that will be provided of people talking about it 10 years after the fact, and the way they still use it in some of the modern games to control their AI. And then almost a completely different kind of thing. This is actually a stateless mode of AI, and it's known as utility theory, the utility theory approach. So rather than having states at all, what we have are just the actions, and we understand how we assign a value or a utility to each action. And that's really kind of tracking the state. So in this case, the state itself is in some cases implicit, and it's actually tracked as a utility on different actions. In the game Stellaris does this. And so what happens is, let's say you start the game and you have sort of default sets of utility for every action possible. Some actions, of course, aren't even possible in the game at that point because you haven't built, say, the right construction yard to build a certain kind of ship, and so that's not possible to build it. But to build that construction yard might be a utility that you have now, right? So to build the advanced ship is a 0 utility at the beginning of the game. But to build the construction yard might be a utility of 8. And building a base might be a utility of 4, and capturing a new planet might be a utility of 10. So the first thing you might do is capture a new planet, right? And that by capturing the planet, now you say, I've captured the planet and I'm going to modify several utilities. So now building a base might be 8, and building the construction yard might be a 10, right? So now we're going to build a construction yard. So we've updated our utilities. We now have building a base as an 8, building a construction yard as a 10, and maybe capturing a new planet is now 2 because for whatever reason, when we've actually captured a planet, we adjust our utility on capturing yet another planet way down, right? So we only want 2 planets so far. So simply by modifying the utility, so every action will modify the utility of all other possible actions. And of course, so let's take it one more step. Build the construction yard, and now we modify the utility on all of these advanced ships as somewhat higher. And so now we can start constructing those ships, right? And so you do this for every possible action in the game, and you have to spend a lot of time tuning those utilities, and especially the utility transition. So not just every time I do something, but also now given what I just did, how do I modify the utilities of everybody else? And so really, in a sense, capturing the utility is the state. So at any given state of the world, it is a utility setting on all of the various actions. And usually in a situation like this, you're always picking the action with the highest utility. So you can go through, and you could probably build out a state machine sort of inverse process to say, well, I start in a state 0 and I have these utilities, and so I know I'm going to pick one or two of these. You can also, of course, pick randomly. So that's another way to do a utility theory approach, is that you pick randomly, but you use a weighted dice to select between the various states. And we'll talk about that because it's a little bit out of scope for what we're doing here. But it creates for some interesting things. And so the game Stellaris is an instance of this approach where they did utility theory through the entire game. So you can compare, say, that against the game Fear, or against some of the other games that we've talked about, or some of the other approaches, and the approaches that we'll do, and see some of the benefits and trade-offs. A lot of the benefit and trade-off, of course, is actually how much work went behind the scenes. And so we'll have some links to talk about some of these things as well in the background. What if we didn't? What if we had our full utility set, but we didn't really want to have to figure out the weights ourselves? Well, that's where you start to come into what our machine learning approach is, right? So machine learning approach knows all of the possible actions, right? So we have, here's all the possible actions of, say, controlling a stick. And we also have a vision of the world through the screen. And what we're going to do is we actually find the weights. So part of the learning procedure of a neural network is to determine the weights for a transition. And so our sort of end goal is to say, well, given the current, what we think is the current state of the world, maybe, or just what we did last time, what is the weight to apply to doing a certain maneuver? And in a neural network, we're always going to pick the biggest one. But what we're going to do is learn the weights, and so given certain activations, or given what we think to some degree the state of the world is, we're going to find the weights that move us to the next state of the world. And so it's really sort of a cross between both understanding an implicit state machine over here by determining what we think the state of the world is, as well as an implicit utility theory, like what is the action that is going to give me the best utility for solving the game. There have been now scientific results where people have run these games and actually managed to get an AI to learn to increase the score simply by looking at the screen and applying certain weights to certain actions. And so you can take this to the fullest level simply by training a machine, right? Unfortunately, to do that properly, you do have to actually train the machine for several thousand hours. I think maybe hundreds of thousands of hours. But given that, the machine is able to learn the weights, the kinds of transitions, the kinds of utility for each action, given more, maybe a more complicated scenario of understanding what the current state does look like, and updating those weights. But it's sort of a utility theory in action, and an implicit state machine at kind of the highest level. And so we're seeing a lot of interesting results come out of that at this point. Again, this is well beyond the scope of what we'll do in this class. You're not expected to create a machine learning. This is more of an interesting point of if we were to sort of argue with Searle a little bit on the Chinese room problem. Well, we can certainly see some interesting kinds of things if we take our state machines and start to advance them much more than what we're doing in our simple examples. So certainly keep that in the back of your mind as you're creating more complicated state machines, or as you want your AI to be more complicated. You simply expand the search space until, of course, it gets large enough that you might have to use one of these alternate approaches to actually create some very complicated behaviors.